Welcome back to che531. In this video, I'll be talking about stiff ordinary differential equations. So for these type of problems, we'll be looking at our generic differential equation that we use for stability analysis, mainly dy dx equals y times lambda. So we're going to be looking at these problems with the goal of understanding the impact of lambda and delta x on the accuracy or stability of the solutions using the numerical techniques we covered so far. So going back to the problem, we're going to define the stiffness as the absolute value of lambda times the domain length. So this is the final point along the domain length xf, and then this is the initial point. So the difference between these two will be the domain length and then times lambda. So overall stiffness will be high if lambda or domain length is large, and stiffness will be small if both of them are small. Okay, so I think to really understand what stiffness is, I think it's good to look at a very well-known problem in the realm of chemical reactions. So we're going to be looking at the Robertson problem, which is a set of coupled chemical reactions. So the Robertson problem, or so-called Robert problem, is described by the set of these three reactions. Imagine A species are converted to B with the rate constant of K1. Let's say 2B molecules associate and give rise to C plus B with reaction rate of K2. And then B plus C, or B molecule plus C molecule are converted to A plus C with rate constant of K3. We can go ahead and write the differential equations for these three reactions, which is going to be a set of differential equations like this, where y1, y2, y3 are the concentrations of the three species A, B, C. And prime here means derivative with respect to time. Okay, so we can go over maybe one of the equations, but the rest of them would be similar. To derive the differential equation for the first reaction, we should be looking at how A is converted to B. So we know that this is a first order reaction, and the change in the concentration of A will be proportional to the concentration of A and the rate constant. But because A is consumed in this reaction, the reaction and the rate of change of concentration of A will be negative due to consumption of A, but will be positive due to production of A from the third reaction. So we can go ahead and write the differential equation. We can say the change in the concentration of A, dA y1 dt, or y1 prime is equal to the negative of K1 times the concentration of A, because A is consumed through this reaction, and then plus K3 times the concentration of B times the concentration of C. So that's why we have K3 times y2, y3. Similarly, for the second reaction, we can say the change in concentration of B, which is y prime 2, is equal to K1 times A, because B is produced from the first reaction. So it's K1 times y1. And then minus K2 times B squared, because B is consumed here through the second reaction. And then minus K3 times BC. So we see minus K3 times the concentration of B times the concentration of C, because again concentration of, or B is consumed through the third reaction. And likewise, the change in the concentration of C is going to be y prime 3. Okay, so this is equal to the concentration of B squared times K2. So that's what it is. And then for the third reaction, we don't get anything because B is consumed here, but is generated on the other side. So the concentration of C doesn't change through the third reaction. Okay, so these are the set of reactions we have. Now let's assume, let's say K1 is a small, K2 is very large, something like 9 orders of magnitude larger than K1, and then K3 has maybe medium range. Okay, now if you want to solve these problems, or problems of this sort where the rate constants are vastly different, then we're going to run into problems, because if the reaction rate is small like that, then our delta T can be large, because the function doesn't decay much, the concentration doesn't change much, so we can march in time much fast. Actually much faster than the case where K1 is large. On the other hand, when K2 is large, then delta T cannot be big, because if it's big, we cannot resolve the density or the concentration of the species over time. So the delta T, which is the interval along the time axis, should be sort of proportional to the inverse of the rate. So if the rate is large, then delta T should be small. And if the rate is small, then delta T can be large. Okay. Now, what if in the problem like this Robertson problem, we have two types of rates, the small one and the big one, and so we basically get stuck here because we don't know what delta T to use. If you use the small one, we cannot resolve the fast reaction. If you use the small one, we're going to use a lot of computational time, which is not necessary for the reaction with the small time scale like that. At the same time, if we use large delta T, then we cannot resolve the variation of species of the reaction with the large rate constant. So that is what we call a stiff problem. Stiff problem is a problem that neither small nor delta T or delta X can be used, just because we have two different mechanisms. One is evolving really fast, one is evolving really slowly, and so we don't know what kind of delta T we use. Okay, and in fact we don't have any choice. I mean, if you use the big one, we create error for the fast reaction. If you use the small one, we're gonna spend a lot of time and not getting the result in a meaningful manner. So going back to this definition, now you see why the definition is like this. Okay, the larger the time period, the larger the stiffness. At the same time, the faster the reaction decay rate, okay, then still larger stiffness. Okay, so the reason that we use actually absolute value of the lambda is because most of the time lambda is negative, because we are dealing with a decaying function usually. So that's why the absolute value. If it's positive, then it's positive, no problem. If it's negative, the stiffness is defined as a positive value. Okay. So here's a table of a comparison how lambda can affect the result. Let's say we solve this this toy problem we had before using the dy dx equal lambda y, right? So let's talk about this toy problem. So in this case, if you want to compare the three methods, the Euler, forward Euler, RK4, and Adam-Moulton, okay? Let's say for lambda equal 0.1, we know that forward Euler is conditional stable, and the condition is that delta x should be less than or equal to 2 times 1 over lambda. So going back to the conditional stability analysis of forward-Euler in this table, so you see that for forward-Euler we need to have a delta x or delta t to be less than 2 over lambda. For RK4 it's 2.8 over lambda. Our delta x should be smaller than this. And for Adam Moulton, there's no limit. Okay, so keeping these in mind, we go back and look at this table. And okay, so if lambda is 0.1, then delta x in forward-Euler should be less than or equal to 2 divided by this, right? Which means yeah, it has to be less than 20, which is of course the case for now. And as we increase lambda, let's say up to about 10, then delta x in forward-Euler should be less than or equal to 2 divided by lambda, which means 0.2. And this is still the case. Now when we go to lambda equal 20, then delta x should be smaller than 2 divided by 20, which is 0.1. And this is exactly the right on the threshold, so we actually need to lower our delta x to be a bit lower than that. So let's say we divide it by 2. So now our delta x satisfies the conditional stability. And from this point on, as we increase lambda, we have to proportionately decrease delta x. I mean, that's the conditional stability for forward-Euler. Similarly, for RK4, we are fine up to a limit, something around lambda equal 10, after which, as we increase lambda, we have to also decrease delta x. Okay. However, for Adam Moulton, because this is implicit method, we do not have any requirement for delta x. We can keep delta x as 0.1 throughout. So there is no change in delta x here. Now I'm going to go ahead and plot log of the error against the log of stiffness. So here stiffness is defined as norm of or absolute value of lambda times the domain length. Assuming that domain length is 1 for simplicity, this S is going to be just the absolute value of lambda. Okay, so we're going to draw the error against the absolute value of lambda in this figure. And in fact, I have a MATLAB script that actually shows this. So let me switch to that one and show you the real output from the MATLAB script. Alright, so this is the output of the MATLAB script that actually solves the same toy problem lambda times y using the 3 methods. So we see that forward-Euler has the highest error. So this is error against the log of stiffness, assuming that the domain length is 1. So I set the domain length 1 in my code. Okay, so we see that the error goes up in forward-Euler as we reach, something around 0.1, because as lambda goes up, then the decay rate is large. And so with the same fixed delta x of 0.1 we had in the table, we cannot really reach a good accuracy. So we're keeping delta x equal 0.1 all the way to somewhere around lambda equals 10. So when lambda is equal 10, which means log of it is about 1, that's almost the maximum we could reach, almost. So this is the least accurate point, maybe along the curve, somewhere around lambda equal 0.1. Okay. Now after this point, we start decreasing on delta x, and that's why the accuracy goes higher, or basically the error goes down again. So the error goes down because we're decreasing our delta x. And that's the same trend with even RK4. So